Okay, today's notes are on graphing linear inequalities with two variables. So the first thing you need to know is that this shaded area up here, this is our solution set. Often referred to just as that, this shaded region or area. So all points in the solution set are solutions. Solutions are an ordered pair that make the inequality true. So here's our inequality. Y is greater than negative 1/2 x plus 1. This right here, this line, is referred to as the boundary line. It separates, or it's the dividing line between the two regions, and it's noted as either a dashed line or a solid line. And we'll talk about these two different ones. The solid lines are with the less than or equal to and greater than or equal to. The dashed lines are with a less than or greater than symbol. So this equation, y is greater than negative 1/2 x plus 1. The first question is negative 5, 1 a solution? So I go over to negative 5 up 1. It is not in the solution set. So no, this is not a solution. And if you wanted to, we could test this out. Negative 5 is our x value, y is our 1 is our y value. So I'm going to replace this. The equation is y is greater than negative 1/2 x plus 1. If I replace these pieces, 1 is greater than negative 1/2 times negative 5 plus 1. Negative times negative makes a positive. Half of 5 is 2.5. So 1 is greater than 2.5 plus 1. 2.5 plus 1 is 3.5. So 1 is greater than 3.5. This is not true. So this point does not work. That's why it's not in the shaded region. The second question, 0, 1. 0, 1 is right here. It is on the boundary line. So because it's on the boundary line, if you look at this and we go ahead and plug this in, we have y is greater than negative 1/2 x plus 1. My y value is 1. Is greater than negative 1/2 times 0. Anything times 0 just goes away, and I'm left with 1 is greater than 1. This is not true. 1 is equal to 1. It is not greater than 1, which is why anything on this dashed line would not be true and not be a solution. 4, 5, right 4 up 5 is up here. If you plug these values in, 5 is greater than negative 1/2, 4 plus 1. A negative times a positive is a negative. Half of 4 is 2. So this becomes 5 is greater than negative 2 plus 1. Negative 2 plus 1 is negative 1. 5 is greater than negative 1. This is true. So this is a solution. So if it's in this shaded region, any point in this shaded region going everything this direction will work every single time for this. And anything in this direction, none of those will ever work. So first, the steps to graphing this. Graphing a boundary line, we use the 2 points. We have to identify the line type. These ones with the equal to, just like what we would graph when it's y equals mx plus b, we would graph with a solid line. So therefore, when we graph with this inequality, less than or equal to or greater than or equal to, those lines are always going to be solid. These two, the less than and greater than, just like this, these boundary lines, you'll end up, if you plug in any of these points, you'll end up with this type of solution. where they would be equal to each other. But because it's asking for less than or greater than, they do not work. So we show this with a dashed line. To shade the solution sets, that's going to be depending on the directions. Less than, these ones, we're going to shade down. Below the line. These ones, these are greater than or equal to, or greater than. That means we're going to shade above the line. So let's go ahead and graph these. So the first thing that we would do is we would graph these in Desmos. I'm just going to build a quick table. The first value I'm going to use here, if I graph this in Desmos, I'm going to go ahead and grab 3 points. And remember, I just want 3 whole numbers. I know for a fact if I use 3 and 6 that I'll get nice, neat whole numbers. When I have this graphed and I pulled up the table, for 0, this would be 5. For 3, this would be 4. And for 6, this would be 3. So 0, 5 is right here. 3, 4 is right here. And 6, 3 is right here. Again, graph this. You won't be able to graph with this inequality. So graph this. Y is equal to negative 1/3 x plus 5 to at least get our line or the location of the line. Now we use this information. First, is it solid or is it dashed? That is a greater than symbol, so therefore it's dashed. So I'm going to go ahead and dash these lines out. The second part, it says y is greater than this value. So over here, we're using the greater than. And this works when it's set up as y and then the symbol. These are set up with y and then the symbol. So if they're in slope-intercept form, then this idea works perfectly. We want all the y values above this set. So here's my trick. I'm going to put my pen where the y-intercept is, and then I'm going to go ahead and shade above it. Cool. Now I'm going to answer these questions. Is 0, 0 solution? I love that they asked this question first because this is always, unless my line is going through the origin, this is always the number I check because it's so easy to use. Here's why. I'm going to plug in 0 for y. 0 is greater than negative 1/3 times 0 plus 5. Anything times 0 is 0. Is 0 greater than 5? No. So therefore, this point right here, 0, 0, is not a solution. Therefore, for shading purposes, I would not shade down. I shaded in the correct direction. 5, 6, if I go over 5 up 6, it is in the shaded region. So yes, it is a solution. Number 2, y is less than or equal to 3x minus 2. So I'm first going to graph this in Desmos. Y equals 3x minus 2. It's going to give me a line starting here with a y-intercept of negative 2 and a slope of 3. So it's up 3 over 1. And it looks something like this. Now, to verify my line, this is less than or equal to. Less than or equal to uses a solid line. So I'm going to connect all of these dots. And because it's written as y equals in this format, I can use this logic right here. It is less than, so I want all of the y values below this information, which is the line itself. I should have done this in pink. So I want all the values below this line. So I'm going to go here to the y-axis, and I'm going to shade down. And you don't need to go all crazy with the shading. Just show that you are shading below that line. So all of the values this way work every single time. I'm going to double check myself with 0, 0. Make sure I shade it in the right direction. 0 less than equal to 3 times 0 minus 2. That goes away. 0 is not less than or equal to negative 2, so it should not be a solution. 0, 0 is not a solution. It's not on that side. So therefore, I shaded in the correct direction. Now it's saying, hey, prove algebraically that 3, negative 4 is a solution. So 3, negative 4 is right here. We know that it works. When it's saying prove algebraically, it means what we just did here. Plug them in. So y is negative 4 less than or equal to 3. I'm going to plug in my x value, which is 3, minus 2. Okay. I don't do anything with the negative 4. 3 times 3 is 9, minus 2. 9 minus 2 is 7. Is negative 4 less than or equal to 7? Yep. There you go. That's proving algebraically. You plug them in and you just use a calculator or just go ahead and use mental math to finish it off and simplify it. 3 is greater than negative 2. Oh, I'm sorry, x is greater than or equal to negative 2 or greater than negative 2. So again, I'm going to graph this. X is equal to negative 2. That's going to give me a vertical line right here. And I messed up because that is a greater than symbol, not greater than or equal to. So this should be dashed. That will still work. All right. And I want all the x values greater than negative 2. So this is the one time instead of shading up or down, I'm actually shading left or right because this is a vertical line. So I want all the x values that are greater than negative 2. Well, all the x values are right here from negative 6 to positive 6. Now I want all the values that are greater than negative 2. So that's all the values this way. So I want all of these values. The first question, is negative 2, 3 a solution? Negative 2, 3 is right here. It is on the line. My x value is negative 2. So is negative 2 greater than negative 2? No. It's the exact same. It is not greater than or equal to. It's strictly greater than. So that doesn't work. Is 2, negative 2 a solution? Well, here's 2. Here's negative 2. Yeah, it's in the solution set. And again, it's just asking about this x value. Is that x value 2 greater than negative 2? Sure is. Ooh, x minus 5y plus 10 is greater than 0. So, me personally, I can't graph this the way that it's given. So the first thing I'm going to do is I'm going to convert it into slope-intercept form. Y equals mx plus b. So, I want to get y all by itself. The first thing I'm going to do is move this 10 over. X minus 5y is greater than or equal to negative 10. Next thing I'm going to do is move this x over. Negative 5y is greater than or equal to negative x minus 10. My last step is I'm going to divide everything by negative 5. That means it becomes y. Negative divided by negative is a positive, so this is 1/5 x. Negative divided by negative makes a positive. 10 divided by 5 is 2. However, we just divided by a negative in an inequality. So instead of greater than or equal to, it becomes less than or equal to. Okay, so when I graph this, I get a y-intercept of 2, and I get a slope of 1/5, up 1 over 5. This is greater than or equal to, or less than or equal to, so this is a solid line. Now here's what I'm going to do. I may have graphed my line incorrectly. What I need to do is make sure I can at least verify that I put the solution set in the correct way. So what I'm going to do is I'm going to test 0, 0. Okay? I go back to the original. X is 0 minus 5 times 0 plus 10 is greater than or equal to 0. All this stuff goes away. Is 10 greater than or equal to 0? Yes. So my solution, 0, 0 would be in it. If I look back at my problem, I said all the y values less than or equal to this line. Well, if I include all of the y values less than that line, that is below that line. So it appears that my solution is going the right way. 0, 0 works. I confirmed it algebraically. It also works in this problem. So that means when I flip this, I did it properly. Is 0, 5 a solution? It shouldn't be. Let's test it out. I'm going to plug this in. 0 for x, 5 times 5. Don't forget that that's negative, plus 10. 5 times 5 is negative 25. Negative 25 plus 10 is negative 15. Is that greater than or equal to 0? No. Good. It's not supposed to be. It's not in the solution set. Doesn't work algebraically from the original problem. If you notice, when I do this algebraically, I'm always going back to the original. I could have made a mistake in here. So always go back to the original. Is 0, 2 a solution? 0, 2 is supposed to be right on the line. It's supposed to be a solution. So let's go ahead and plug it in. 0 is my x value, minus 5 times 2 plus 10. Negative 5 times 2, that's 10. 10, negative 10. Negative 10 plus 10, that's 0. Is 0 greater than or equal to 0? Yes, and it's right on the line like it's supposed to be. So yeah, everything looks like we did it correctly. This problem right here is the most complicated one because you have to convert it into slope-intercept in order to graph it. But we go through our normal process of converting to slope-intercept, and even if you would have messed up this part right here and forgot to flip it over, if you graph the line and tried these points out, these 3 points, 0, 0, 0, 5, and 0, 2, well, 0, 2 is going to work every single time because it's right on the line. But 0, 5 and 0, 0, that could have verified, oh, I'm supposed to shade down, not up. So you'll notice whenever we're working through these inequalities and we're graphing them, you'll notice that I will often use the point 0, 0 because 0 times anything is 0 and it's just easy to use. The only downside is if it ever goes through the origin itself. Okay, those are notes for graphing linear inequalities with two variables.